Okay, so this week we're going to bring things around and we're going to take the stuff we did with absolute values and extensions of QP, so extensions of complete fields, and we're going to bring that back around. We're going to look again at number fields, so extensions of Q. And we're going to see sort of how absolute values and the things we learned about them in this sort of complete case help us understand properties of number fields. So I just want to start by recalling some facts before I state the main theorem of the day. So recall. So if K is a number field, so meets the finite extension of Q. And then if I look at the ring of integers, OK, and I look at a prime ideal, a non-zero prime in OK, then I can form the localization of OK at P. So this is the localization at P. This is a discrete valuation ring. And so in particular, if I look at sort of the prime ideal corresponding to sort of generated by P inside of here, so P times OK P, this is the only non-zero prime ideal. So this is a local ring with a unique maximal ideal and unique non-zero prime ideal. This is just sort of generated by a single element pi. Good, and so then I define the absolute value corresponding to P, while just using that K, which is the fraction field of OK, but it's also the fraction field of this localization. I mean, somehow this just localization inverts some things, and then you sort of invert the rest to get K. And so anything in here, if I have some element A and K, is written uniquely as A to the n times, sorry, not A to the n. A is equal to pi to the n times u, where pi was the uniformizer, so it's the generator of this sort of unique prime ideal. And then n is just some integer. So since I'm in the fraction field, this integer can be negative. Yeah, maybe I should have written an additional thing here. So the point is sort of that the last thing you have left to invert when you go sort of from OKP to K is 1 over pi. It is just use that, sorry, you have pi left to invert. And so this sort of other thing here, this U is sort of something in OK P cross. So this is also something we've seen before. I just want to recall it. And then we define sort of the sort of frac P attic absolute value, so absolute value attached to this prime ideal, just to be C, well, okay, C to the minus n. So this n is this n, so just the power of pi dividing it. So you want this to be small when n is big. So and here when we write this, usually we mean the normalized absolute value. So this is just for C. So we need to take just some base to get absolute value. We just need to take some base greater than 1. And so, but here we sort of take the normalized absolute value, which is where we take C to just be the size of the residue field, which is the same as the norm of P. Okay, so that's the definition of the absolute value attached to a prime ideal. Let me just call sort of this is equivalent. Sort of any c greater than 1 will give an equivalent absolute value. So when this comes up today, we'll sort of actually what will come up will a little bit more naturally will be an equivalent absolute value. But okay, so the reason this is called the normalized absolute value, you'll see when you look at the worksheet this week about the product formula. So this is okay, but let me just leave it at that. So the point is this C isn't actually so important, the specific choice. You get an equivalent absolute value if you take sort of any C greater than 1. Okay, so I just wanted to recall that statement. And let me sort of just make the observation which is so you have some element A in OK, then sort of the absolute value of A, the p-adic absolute value of A is less than 1. So the frac p-adic absolute valuation is less than 1. And this is just the same as saying that A is contained in the prime ideal generated by P. Sorry, not prime. A is contained in the prime ideal P, frac P. Means somehow, well, okay, if you sort of chase through the definitions, that's literally what it means. Okay, good. And another way to say it is if you sort of take the ideal A and you sort of write down its factorization, then sort of positive power of frac P appears in that factorization. So in particular, so there's okay, so if I have P, if P sort of divides P, so P is the ideal generated by a prime number P, which is, and so this is the same as saying P intersects Z. So frac P intersects Z is just a prime ideal generated by P. So it's this corresponding this actual integer prime number P. Then the absolute value of P is less than 1. So somehow this is just saying, okay, if I have some prime, its intersection with integers is some prime ideal in the integers. Well, that's just generated by some P, like actual prime number P. And well, if it's in, but that just means P is in this ideal, and so has absolute value less than 1. So, and this implies that the absolute value. So if you just then use Ostrowski's theorem, which sort of classifies all of the absolute values on the rational numbers, well, there's only one of them where P has absolute value less than 1. And that's the p-adic absolute value. So, okay, so if you have a prime sort of that sort of appears in the factorization of P, then it really is giving you the p-adic absolute value. So that sort of is really giving, again, then sort of, let me say the way, so if you have a prime that lies in the factorization of P, it's really giving you some extension of the p-adic absolute value. Okay, good. So we'll come back to sort of some other things related to this in a moment. But now I want to sort of state the main results of today, building on this. Okay, so let's let K over Q be a number field. And let P be a prime number in Z. So be an integer prime. So prime in the traditional sense. And let me just write down the factorization of the ideal P in OK. Okay. Then the result is, if I take this field K, and then I can extend scalars to QP, so I just tensor over Q of QP. So now I get sort of some QP algebra, so not necessarily going to be a field. It won't be a field, but I can say actually exactly what I get. I'm going to get the product from I equals 1 to m of K sub frac pi. So this is sort of running over all of these factors, and then I'm getting K sub frac pi, which just means the completion of K with respect to this absolute value. Induced by that prime ideal as above. Okay, so this is most of the theorem, and then I should say a little bit more. Moreover, so K pi over QP has ramification degree E equals EI, and inertial degree F equals Fi. So remember, sort of ramification degree is just sort of, and it makes sense for any extension of discrete. It makes just as much sense for an extension of QP as it makes sense for an extension of Q. Somehow you look at ZP as the ring of integers, and you look at ZP inside of QP, and then sort of the ring of integers in here is extension of that, and then you look at sort of it just has a single, but as just a single prime ideal living above P, and then you just look at sort of the degree of the residue field extension that could do this F, and you look at the sort of power of that prime ideal dividing P, so the prime ideal in ZP, and you get E. And the point is sort of, somehow doing this completion, like it didn't change these numbers from what you had over here. It sort of just picked out the ith one when you completed the ith place. Okay, so that's the main result. So what does this say? Well, let me just make a quick observation. This is like sort of what happens for K tensor over Q R. So, and this is something we've used many times before, and this is sort of how we actually motivated the introduction of sort of looking at p-adics and things, maybe 2 lectures ago. But I mean, this sort of looked at like a product over all of the embeddings of K into, well, okay, this is like a product. So this is isomorphic to R to the R1, the R to the R times C to the S. So, and so each of these are the completions of K for the different sort of extensions of the Archimedean absolute value. So if you put an Archimedean absolute value on K, well, it restricts to an Archimedean absolute value on Q inside of K. And so then sort of when you complete, like you get something that contains the real numbers. And so that's either going to be the real numbers or complex numbers. And sort of somehow you can sort of rephrase that by looking at this tensor product. So we'll come back to that in the p-adic case again today, and we'll mind how that's done. But okay, so this statement is some analog of that. The only difference is sort of, and again, we just sort of, there are more, so we don't have like a weight. There are only finally many sort of p-adic fields of any bounded degrees. So that's sort of something we saw. So and somehow like you should think there are only like finite many possibilities for this case of pi over here, but like we don't have a nice simple way to write them down for an arbitrary p. So, but okay, they're the same kind of thing where you're sort of taking something global that's complicated and sort of replacing it with something sort of local that's small, that's sort of simpler to understand. Okay, so that's sort of one remark I wanted to make. Let me explain a couple of applications of this that will sort of help us think a little bit more about what it's saying and how it relates to this statement. So let's do corollary. Let me write it this way. So if alpha is contained in, so if alpha is contained in K, then the trace from K over Q of alpha, just the product, or sorry, the sum over all from I equals 1 to M of the trace of for these local extensions. So the trace of alpha sort of breaks up as sort of this trace over these local extensions. And similarly, sort of the norm of alpha breaks out as the product over the norms for all these local extensions. Okay, and well, you could say the same, and these traces and norms, like these are coefficients of the characteristic polynomial for alpha acting by multiplication on sort of the Q vector space K. And sort of that, those don't change if you sort of extend scalars to the real numbers. They don't change if you extend scalars to the p-adic numbers. And so this is sort of just, but then sort of in each of these factors is some subvector space that's sort of preserved by multiplication by alpha. And so, okay, so that's sort of where this comes from. And then we used these identities before. Instead of for the p-adics, we use them with tensoring the real numbers. Like this trace statement was sort of what let us sort of get a handle. This trace statement sort of combined with this, like that's what let us get a handle on discriminants and sort of think about discriminants sort of using lattices inside of here. And in fact, one of the biggest reasons to sort of use this identity is to get the same, to get sort of similar control over discriminants, but sort of to get this control over the power of p dividing discriminants. So sort of this first one implies, in particular, the power of p dividing the discriminant of K over Q, which is sort of really means discriminant of OK over Z, is equal to the power of P dividing the products of the discriminants of KP over QP, which really means sort of the product of the discriminants of, here it's sort of less ambiguous, but OKP over ZP. Okay, so I mean, so, and it's again, it just comes from sort of this locality of the trace. This gives you sort of locality of the discriminant. But in somehow this is really useful because it tells you, so you can break down to sort of some simpler computation to get the power of P dividing discriminant that only sort of depends on these local terms. And so on your homework, you'll see a problem that sort of lets you sort of show that there are only finitely many there are only finitely many extensions, but only finitely many number fields sort of degree less than n and sort of that are unramified outside of some finite set of primes. This is some very important finiteness theorem in number theory. Okay, but you'll see that on the worksheet, so you'll explore this little bit more. I just want to sort of highlight, so we talked about discriminants and sort of varying degrees of generality. The discriminant of a number field is sort of pretty special because it really just, the discriminant like of k over q, like this is pretty special because or OK over z rather, like you really just get sort of a well-defined integer. Like the discriminant of OKP over ZP, this is not sort of like you don't get something well-defined, you sort of get something well-defined up to squares in ZP. But sort of something, sorry, up to squares of units in ZP. So, but somehow the square of like that means sort of the power of p is sort of well-defined because sort of multiplying by the square of a unit in ZP doesn't change the power of p. So somehow this is sort of the best thing you can, and close to the best thing you can sort of hope to get over here about this information. But and sort of now if you sort of do this at sort of every single prime p, you're going to get so if you do this for every single prime p, you're going to get sort of everything about the discriminant. So that's pretty good. Okay, so that's sort of the first corollary of this statement. The second sort of, okay, maybe this is sort of less a corollary, more of an application. Of the theorem. Which is basically sort of you reduce sort of factoring P into prime ideals in OK to factoring polynomials sort of in some sense. So, and again, this was one of our main motivations. One of the ways we motivated introducing the p-adic numbers is sort of, we'd already seen that like in certain situations, like when a ring of integers is monogenic, you could understand the factorization of a prime ideal by looking at the factorization of sort of its minimal, like the minimal polynomial of a generating element mod p. So that was sort of our main tool for computing factorizations. But when we sort of spent some time discussing this annoying fact that that doesn't, well, it's the worst in some sense, but like the process doesn't work so nicely. Like it's not sort of about factoring a polynomial anymore if the ring of integers is not monogenic. So this statement in some sense corrects for that. At the price that instead of factoring polynomials mod p, you're sort of factoring a polynomial over qp. But somehow we've seen that's not such a bad thing. Like we have, and that's one of the emphasis is the last couple worksheets is that we have Hensel's lemma. We have like this Newton's method enhancement of Hensel's lemma. So we have tools that we can use to factor polynomials over qp. So it's sort of maybe not as frightening as it first seems. And so let me just sort of explain this. Well, sort of the theorem says, here's why. The theorem says sort of K tensor Q, QP is the product of sort of these completions. But if I write K is equal to Q join alpha, so I sort of pick some primitive element, which I then think of just being Q of X mod the minimal polynomial. This here is the minimal polynomial of alpha. And then I factor f over qp. So f of x equals, let's say I equals 1 to s of fi of x. So fi of x irreducible in qp brackets x. So I factor it over QP. So I sort of it's irreducible over Q, but it might and it may and sort of often will factor when I sort of allow coefficients in QP, just like if I allowed real coefficients instead of rational coefficients, this would sort of almost always factor more. Okay, so if I do this, then, well, I get that K tensor QP is also isomorphic to QPX mod f of x, which is QPX. So that's just our sort of standard trick. Mod the product from I equals 1 to S Fi of x, which by the Chinese remainder theorem, I mean, each of these Fi's is irreducible and F is separable, so they have to be distinct. And so this is just the product of QPX mod Fi of x, and each of these is a field. So in fact, I mean, the theorem says, so we must have K, so we must have sort of I equals S and, or sorry, S is equal to M. So the number of factors of this polynomial is the same as the number of primes lying above P. So just because we have this product into M fields and we have this product into S fields, so sort of S has to be equal to M. And up to reordering, we're really going to have that sort of QPX mod Fi of x is equal or isomorphic to KPI. Okay, so somehow, okay, then this is already something. So this tells us at least that the number of primes, this tells us at least sort of like the number of primes in the factorization of this polynomial f over qp is the number of primes dividing, it is the number of primes dividing p. I mean, somehow like, and what we're saying is sort of like if you sort of have the presentation like this, like we have tools for sort of factorizing f. So and this is sort of like this thing is something you could sort of hope to compute in some generality. And then sort of that tells you like how many primes there are. I mean, you get more because, and you also sort of have, then once you do that, you also sort of have some presentation for sort of each of these extensions. And so this other part of the theorem says, like the ramification and inertial degree just come from this local extension. So now you sort of have some sort of local extension, which you can try and compute the ramification and inertial degree of. And so here, for example, and one nice thing about this extension is, let me just sort of say, like note, so the ring of integers here is monogenic. I mean, maybe not by this Fi of x, but sort of by some, there is some generator over CP. So, and once you do this localization and this completion, like your ring of integers is monogenic. So this is explained, and this is one of the exercises on last week's worksheet. But so somehow like, and you really could, like now this ring of integers is monogenic, and you could use our standard sort of mod p tools over here, sort of assuming you can find some generator to do this factorization. So you really also sort of somehow reduce the factoring polynomials again to get EI and FI. Okay. So so this application of the theorem sort of really, and somehow it sort of connects back to why our motivation for introducing this stuff in the first place. It sort of lets us sort of relate the factorization of P to factoring polynomials sort of unconditionally by sort of working with the p-adic numbers instead of working mod P. And so somehow the point is like, where the p-adic numbers, you've sort of, it's like working mod P, but you just have finer information because sort of things don't become zero when they're divisible by P, they just become small. And that gives you a lot more flexibility when working around. And well, it's the right amount of flexibility for sort of understanding factorization of prime ideals, it turns out. Okay, so this is sort of a nice application. Okay, but so now I want to prove the theorem. So let's just look up and see what we have. So just to recall the statement of the theorem, it says I've got a number field, I've got an integer prime, and I want to sort of look at its factorization in OK. And then I'm going to match up that factorization sort of with the completions that sort of appear. Sorry, the completions sort of for the primes in that factorization are sort of what appear when I tensor with QP. And sort of then I have this identity of ramification degree and inertial degrees. Okay, so we'll use the second part when we prove the first part. So let me sort of prove the statement of the second part first. Well, actually, yeah, so I might swap around how I'm going to organize it. So let me sort of prove sort of two lemmas first. So one of them will be that one, but maybe I'll prove another lemma first. That's sort of a lemma that's sort of, I guess the first lemma I'll prove will sort of go in the opposite direction of this thing I did here. So it'll explain sort of why we can go from an absolute value back to a prime in OK. Whereas here we sort of start with a prime in OK and sort of then went to an absolute value. Let me do that one first. Okay, so lemma. Lemma 1, I guess. So suppose L over QP is just any finite extension. And so I have this number field from before. Okay, number field. And I have an embedding. Let me just write iota. Embedding name iota from K into L. Then the absolute value so I get sort of an absolute value by just taking the absolute value on L. So on L, I have sort of the unique, so L is a finite extension of QP, so we know it sort of has a unique extension of the p-adic absolute value. So I can sort of take that absolute value on L, and then I can just sort of restrict it by this embedding to an absolute value on K. So then maybe I'll just write the p-adic absolute value. So here I have the p-adic absolute value on L. And I just mean the sort of extension of the p-adic absolute value of L. So I'm trying to write my p as just a normal p. On K is equivalent. So this absolute value to one of the form the absolute value is sort of attached to some prime ideal P of OK, or P some prime ideal that divides. So fact P is the prime ideal that divides integer P in OK. So I was saying if there's any way at all to sort of put my field K into sort of some extension of QP, well then actually it's coming sort of from somehow the absolute value I get from that is one of these absolute values coming from just a prime ideal above P. So it's sort of coming from this algebraic source. And moreover, let me just say the closure of K, so like closure in the topological sense. So maybe I'll write it. Inside of L, so let me write iota k. I just start think of k as being a subfield of L via iota is sort of so it's identified sort of canonically with the completion of k at this sort of prime ideal P. Okay, so good. So I mean, somehow this is so this is basically equivalent to Ostrowski's theorem for k. So I'll say a little bit more after that. But we're saying not only the prime ideals give absolute values, but really sort of, I mean, some of this is very close to saying that every absolute value comes from a prime ideal. And I'll after I state the lemma, I'll sort of say that a little bit more. After I prove the lemma, I'll say that a little bit more precisely. Okay, but this is one of the tools we need in the proof of the main theorem as well. So let's go through it. Okay, so let me sort of first observe. So note that for sort of A contained in OK, so if I have something in the ring of integers of K, then the absolute value of sort of iota of A is less than equal to 1. So this is just because A is integral over Z, and this is true for any integer. Any integer, its p-adic absolute value is less than equal to 1. This was an exercise. This was basically an exercise last week. And so here, I mean, of course, you're using that this is a non-Archimedean absolute value. But good. Okay, so good. So everything in OK has absolute value less than equal to 1. And moreover, I can just define a prime ideal. Frac P is just going to be all of the A in OK, such that the absolute value of A is less than 1. So I take this ideal consisting of all things with absolute value less than 1, and well, and basically just from the definition of an absolute value, so it's fairly obvious this is a prime ideal. Like if you multiply two things together and the absolute value is less than 1, then sort of one of the two things has to have absolute value less than 1. Okay, good. So this gives you a prime ideal. And sort of because somehow because sort of we're looking at the p-adic absolute value, like P has absolute value less than 1. So P is definitely contained in this prime ideal, but that sort of is equivalent for a prime ideal in ring of integers to saying that this intersection is the prime ideal P. Okay, good. So good. So in this, well, this prime P is then our candidate for sort of the prime that should be defined in absolute value. Okay, so we just sort of need to check that this absolute value really is equivalent. Like this sort of this absolute value here is sort of equivalent to the like frac p-adic absolute value. So let's do that. Okay, well, so if I have A contained in, so if I have some element A contained in K, then I can write sort of A is equal to pi to the n times U, where sort of P times OK is equal, so P times OK localized at P is equal to pi, and U is in OK localized at P cross. Good. And then right, and well, I want to know what the absolute value of A is. Well, I claim the absolute value of iota of A P is just going to be the absolute value of iota pi. Okay, it's going to be the absolute times absolute value of iota of u. But this is going to go away because it's going to be equal to 1. So you're just going to get sort of this part. So why? Well, because if you just think about what I've inverted, I mean, sort of u is an OKP. Sort of, yeah, so u is in sort of this OKP cross. But that means I sort of, and so when I sort of form this, what that means is sort of when I sort of localize at P, that means I'm inverting everything outside of the prime ideal P. But so that means sort of I'm only like everything has absolute value less than equal to 1 that's in OK. And then I'm inverting things that really have absolute value equal to 1, because if they had absolute value less than 1, they would be in P. So I'm sort of only inverting things that have absolute value equal to 1. Okay, so sort of somehow everything in sort of OKP still has absolute value less than equal to 1. And so, okay, so, and then it's not so hard to see from that the units are the ones that have absolute value exactly equal to 1 in there. And okay, so this sort of the absolute value of the unit is equal to 1. Okay, so good. So this works out. Okay, but so and basically then I just need to check that this sort of has. So it just remains to check and to see that this is the sort of the same as like the frac p-adic absolute value. I just have to check that this is greater than 0, greater than 1. So this would be minus n. So it's I pi to n. So I need to check. Sorry, I need to check just that sort of iota of pi, sort of p-adic absolute value, is less than 1. Okay, like this is sort of checking like the c is sort of greater than 1. Okay, but and well, that's easy because sort of like pi to the e is, so pi to the e times OKP is equal to p times OKP. Okay, and then so that means sort of the absolute value of pi to, so these differ by a unit in OKP, so they have the same absolute value. So absolute value of pi to the e is equal to p. Sorry, so the absolute value of iota of pi to the e, the absolute value of p. So this is, it says that the absolute value of pi, p to the e is 1 over p. So absolute value of pi, iota of pi, is just 1 over p to the 1 over e. Okay, so this is less than 1. And here sort of e was the ramification degree of this prime p. Okay, and that's what we want to check. So that tells you that this is equivalent to, this sort of frac p-adic absolute value just by sort of comparing with this initial definition. I mean, you'll get that sort of something's less than 1, sort of if and only if sort of this n is positive for both of these two absolute values. And that's sort of one of the criterion that meant two absolute values were equivalent. Okay, so that sort of proves the first part, that if I have an embedding into an extension of QP, like the restriction really is the frac p-adic absolute value, or equivalent to the frac p-adic absolute value for some prime p, for some prime dividing p. Okay, and then the last thing is the closure in L is KP, but well, I mean, that's essentially trivial. Like you just think through the definitions. I mean, L is complete for this absolute value. And so the closure is just the completion of K for this sort of induced absolute value, which is by definition sort of this K sub P. Okay, so this last sentence sort of follows for free from the first part. And the fact that sort of L is complete. Okay, good. So that's this lemma. Yeah, and so yeah, so let me sort of finish with the mark I sort of started before. So this proof sort of basically gives Ostrowski's theorem for K. So recall sort of Ostrowski's theorem for Q says that Ostrowski's theorem for Q says that the only non-trivial absolute values on Q are sort of the p-adic absolute value for prime P or the Archimedean absolute value. And so we didn't prove this, but we stated it. And if you look in Milne, sort of you basically prove this by elementary means for Q. But now sort of you can sort of use the same kind of argument we just did to bootstrap up to sort of prove Ostrowski's theorem for any number field. So sort of equivalent to Ostrowski's theorem for any number field would be like any absolute value on K is sort of either like the frac p-adic absolute value for some prime ideal frac P, or it's sort of coming from an embedding, it's an Archimedean absolute value coming from an embedding to real numbers, complex numbers. Well, if you have a non-trivial valuation on K, sort of it's going to restrict to a non-trivial valuation on Q. So it's a good exercise to think about why that restriction has to be non-trivial. And then, so if that restriction is p-adic, well, I mean, somehow that means that K is sort of going to, like, the completion for that absolute value is a finite extension of QP. But now, sort of this argument we just gave tells you that that finite extension sort of is actually sort of the completion sort of for some prime ideal of OK. So this gives you the sort of finite place part of Ostrowski's theorem, so that for the primes of OK, and then for the sort of infinite places, so for the sort of Archimedean absolute values, you have to use again that sort of the only sort of, you just have R and C are sort of the only complete Archimedean fields. Okay, so that's how you get Ostrowski's theorem this, but that's sort of not the main thing we're focusing on right now. So good. Okay, so we have this lemma that if you have a finite extension of QP and sort of embedding K into it, then sort of the absolute values you get are sort of equivalent to frac p-adic absolute value for some prime dividing P. Okay, and then let's do the next lemma. Which says, so it's basically going to verify sort of the second part of the theorem, right? So it's going to sort of say that sort of the ramification degree, the inertial degrees sort of can be computed locally. Let me make that precise though. So this says if, okay, so again, K is a number field, and P is equal to P1 E1, PM to EM in OK, then P times O. Okay, so if I look at how the prime ideal P factors in the ring of integers in the completion, so remember ring of integers completion, sort of all things have absolute value less than equal to 1. Then this is just going to be equal to sort of P1 Pi to the EI times OK. Which is really sort of going to be equal to pi to the EI times OK. EI, or sort of P, okay. So the notation can be a little heavy, but let me just sort of write down and I'll explain it. So I'll say pi I. So it's important to sort of distinguish between two things. Here, this is the localization of the ring integers. This means just invert everything outside this prime ideal. And here, this is and then here, this is sort of the completion. So sort of, you can localize first and then complete somehow. So sort of like this sort of lives inside of this, but in sort of some substep. But anyway, we sort of know once we localize, this prime ideal sort of gets generated by a single element, so it becomes principal. And so in particular, it's sort of is still principal when we sort of pass the completion. Okay, and sort of furthermore, OK pi mod pi OK pi is isomorphic to sort of OK mod p OK mod p. Okay, so in this, so this first part, this says EI is equal to E in the theorem, and this second part is what says sort of FI is equal to F. So somehow this is saying the residue field doesn't change at all. So sort of the degree of residue field extension also doesn't change. So you just sort of pick out this one. And similarly, sort of the ramification sort of doesn't change when you sort of pass this completion. And this is saying as part of the theorem where you can really detect the sort of the residue field extension, its degree of this F, and sort of the degree of ramification sort of by passing to the completion. Okay. The proof is pretty simple. It's just sort of, and the proof is, and as almost like immediate, you just have to sort of think through, but you have to be a little bit careful to sort of write it down really precisely. I mean, you just have to think through what these statements mean, and somehow just remember that sort of all of the theory of Dedekind domains applies to sort of the extent, the local extension of OKPI over ZP, just as well as it applies to the global extension of sort of OK over Z. Okay, but and somehow, so the proof is just sort of like the corresponding fact is true if we sort of just pass to the localization. And somehow sort of everywhere here I wrote OK comma PI, so the localization instead of the completion. And then sort of just nothing really changes after, nothing about either statement changes after completing. I mean, okay, so it's sort of two things going on there. And first, like somehow, like completing is sort of refining what you see when you do mod P, but well, somehow P is an open ideal, so like you're not going to sort of change what's happening mod P, and so this is basically a sentence that P is open, so you're not going to change this, the mod frac P. And then, I mean, one way to think about sort of why the ramification degree doesn't change is sort of, I mean, like the absolute value, I mean, some of the ramification degree, you can think of it like in sort of this previous exercise. So if it's encoded in just like, what is the absolute value of pi? And sort of, I mean, so the absolute value of pi isn't going to change when you sort of complete. Okay, so that's, I mean, so depending on sort of how obvious this is to you, it might be worth thinking through a little bit more carefully, but I don't want to sort of do it. I mean, probably you benefit more from thinking through this carefully yourself than through me sort of saying too much more about it. So let me just leave it at that. Okay, but so that's the second lemma, and then let's prove the theorem. Okay, so let me just sort of scroll back up to it again so we can see it before we prove it. So we have K over Q as a number field, so a finite extension of Q. P is a prime, an integer prime. The factorization of P in OK into prime ideals. And we're saying that K, when we tensor of QP, we just get sort of the product of all the completions with respect to the prime ideals that lie above P. And then we've sort of this moreover part we've already proved. That's what the second lemma proved. And this moreover we're going to use when we prove this. Okay, so let's do it. Okay, so so we're looking at K tensor Q QP. And let's take a primitive element, so K is equal to Q alpha. And then we just write that as sort of Q of X mod F of X. So just like we did in this application of the theorem, actually. So actually sort of this application of the theorem is somehow plays a role in the proof of it as well. And then we're factoring, so we're going to factor F of X into product I equals 1 to M. So S, here, sorry, of Fi of X. So we don't sort of a priori, in that application, we knew S is equal, we sort of deduced S was equal to M, but we don't sort of know that beforehand. So we're going to prove that along the way. So that sort of the number of factors here is equal to the number of primes. Will show up along the way. Good, and so then we get, so this is in QP of X. So in polynomials for QP. Okay, and so then we get sort of by the same reasoning, this K tensor Q QP is just isomorphic to the product from I equals 1 to S of QP X mod Fi X. Okay, so now what happens? Well, so for each I, and in particular, just sort of by taking this isomorphism and then sort of projecting onto one of the factors, you get a map from K into QPX mod Fix. So it's an injection because every map from a field to another ring is an injection. Okay, and while the image is dense, because somehow in alpha goes to X, sort of think about what all these maps mean, like alpha goes to X, and so sort of you have sort of Q brackets X inside of here. And this is dense in sort of, what do I mean dense? In sort of the, yeah. Because sort of QPX mod Fix, this is a finite extension of QP. So sort of it's complete and has an absolute value. So it has an absolute. Sorry, I'm having troubles. Let me try this. This is a finite extension of QP. Let me just write that. So, and this is a finite extension of QP, so it has an extension of p-adic absolute value, and it's sort of complete with respect to that. So it has a topology, and it's complete with respect to that. So the image of K is dense in there, just because when somehow like you contain alpha and you sort of contain, yeah, okay, and you just, maybe this is a good exercise sort of to see how well you sort of understand why there's an absolute value on here. But okay, the image is dense, and the point is just sort of you contain sort of the image of Q brackets X in here. Okay, so good, you get this map of image dense, and so that means sort of by the second lemma, or so by lemma 1. So what did lemma 1 say? In lemma 1 said, if you sort of can put K inside of some finite extension of QP, so here this L is sort of QPX mod Fix, then so the absolute value you get from that is just sort of a frac p-adic absolute value, and the closure of the image is sort of just the completion. But now in this setting, because the image is dense, and the image is dense, so the closure is just everything. By lemma 1, we get that QPX mod Fix is equal to sort of K completed at Pj for some j. Okay, good. So we get sort of get this, and this isn't just sort of as like abstract fields. Like this is sort of as fields with an absolute value. Okay, good. So good. So that works for each of these i's. I claim sort of we get distinct. So distinct i's give distinct j's. Okay, so why? Well, you know, when we have to show sort of, we need to show the induced topologies on K are sort of for two different i's are different. So that would tell you we were getting inequivalent absolute values, and so sort of they couldn't sort of be the frac p-adic, pj-adic absolute value for the same j. So, but how do you do that? Well, I mean, let me just sort of say like, okay, so, well, if just take polynomials, let me say gij of x that sort of go to fi. So these should be in q of x. They should sort of approximate fi in qp of x. So this should be as j goes to infinity. So I'm going to take polynomials with coefficients and rational numbers that approximate this sort of fi. And then so it's not so hard to see that sort of fi exercise maybe. So this gij of alpha, this is going to go to 0 as j goes to infinity, sort of in qpx mod fi of x. So if I sort of look at the image of this in qp of x mod fi of x, well now sort of, so this is just going to gij of x, and that's going to fi of x, so it's okay, so it's approaching 0. But not in sort of any other qpx mod fi prime of x. Okay, so somehow in this, what's just going to go to sort of the image of fi of x in here, which is sort of not 0. So okay, so we have some sequence of elements that goes to 0, sort of in one of these, but in sort of one of these topologies, but sort of not to 0 in any of the other topologies. So that means sort of all of these topologies are really, that means so this topology is really distinct from all the other ones. So now you just apply this to all the i's. So okay, you really get distinct topologies. So that means sort of really these factors are sort of mapping injectively into the primes. And then we just have, okay, so now we need to see why we get all the primes. But I mean, here we just use so see we get all the primes dividing p. Just use that the dimension of K as a Q vector space. Well, that's just by definition K colon Q. This is, I mean, so I know from our work before that this is the sum I equals 1 to m of EI times FI. On the other hand, sort of extending scalars from Q to QP doesn't change the dimension. So this is the same as this dimension. This is the sort of sum And well, this is going to be the sum. And so this thing serves as the product of these fields. So this is again, QP x on FIX over QP. Okay, and now I sort of know, like this is sort of some subs. So each of these is sort of isomorphic to some equal. Okay, right this way. So I get sort of some Pj sub I for QP. Okay, and so this is, but then sort of, okay, so yeah, good. So applying this second lemma too, this is just, and this is the degree of Kp sub ji over Qp. And so this is sort of E j sub I times F j sub I. This is lemma 2. Okay, and so, and this is sort of this sum is sort of giving me some sort of strict subset of this sum. I'm summing over some strict subset of the things over here, but I'm getting the same thing. So I need S equals M and hitting everything. So I know I can hit each thing only once. So I said before I just had S was less than M, but now I really see I have to hit everything. So that's sort of how I can see that I'm really getting all of these fields. Okay, good. So I'm done. That proves the theorem. Okay, good. So yeah, great. So somehow, and this will be useful on the worksheet this week, and it's actually, and some baby case of this came up on the worksheet last week, and a lot of groups didn't get to that. So I made the worksheet this week a little bit shorter, so people have time to go back to that. But in some, and this is very powerful. Like, I'm like in the worksheet last week, and sort of even before that, like, this is sort of how a good way to come up with like using this statement of this theorem. For example, it's a good way to come up with examples of polynomials sort of that generate extensions that aren't monogenic. So that's sort of what some of the exercises are about, or what one of the exercises last week was about, sort of building on an exercise far before that. But you can use it to construct counterexamples, but actually the point is sort of it's robust enough to handle like this non-monogenic situation, which is sort of nice. Of course, it's useful for many other things. Like in particular, this sort of corollary we gave about the discriminant and sort of the finiteness theorem you'll prove on your worksheet. Like these are other sort of very important consequences of this method. Okay, I think we will stop. Yeah, we'll stop there for today. Thanks.